crystal in your brain.
Yeah.
Positives surrounded by negatives, and those are surrounded by positives, and you've got this three-dimensional network of ions all attached. What is it going to take more energy to cause to melt? A covalently bonded solid or a ionically bonded solid?
Ionic.
Ionic bonds they all have high melting points. It takes more energy to melt an ionic solid than it does just about any covalent.
Is it because that's
Because what? Yes, it is. Here's what I want you to know. When you have to compare any molecular compound that has covalent bonding, its melting point, to an ionic, pick the ionic. You wrote at the beginning of the chapter, it's in your notes, ionic compounds have high melting points. That's what I'm talking about. Ionic compounds have much higher melting points than covalently bonded ones. I don't know that this is true, but I would say anytime I'm given a choice between any ionic compound and any covalently bonded compound, I'm going to choose the ionic for having the higher melting point.
Network covalent.
Except for network. That's right. Watch out for those network solids. I warned you about that too. Silicon dioxide, diamond, right? Yes, ma'am? Oh, Benita, you get another question now.
Two actually.
So I'm really confused.
Okay.
So you have the highest boiling point, which means it's harder to turn into a gas.
Yep.
The highest freezing point means it's harder to turn into a liquid. So then,
So which would take the highest, the most amount of energy to try and change into a liquid?
okay, so then the lowest freezing point, which means it's easier to turn into a liquid.
Where's lowest freezing point? Yeah. Oh, down here. Yeah.
So it's easier to turn into a liquid. And lowest boiling point means it's easier to turn into a liquid. Yeah. So you want to go really lower, exactly, lower polar first. For those.
Yep.
So it's
Yep.
not anything else like
So for the lowest freezing point, you're looking for the thing that has the least intermolecular charge. Okay, so B is NaCl. Now listen, the solution guide is your friend. And make sure when you're doing these, you do it, give yourself a particle model, what is happening, what's going on with the intermolecular attractions. All these have to do with intermolecular. And then read the solution guide and make sure that you understand what it's trying to tell you. It'll describe what the particles are doing and why the right answer is right. Mohammed. Oh, wait, we gotta go. Hurry up, Mohammed.
We're not talking about the bonding to it and CL, we're talking about like one and CL.
That's right.
So like,
Yep.
so why?
Ionic compounds always are held together more tightly than covalently bonded. All of them.
Right, but if we're melting it, it's not gonna break up NaCl.
Yeah, eventually you have to break the Na away from the Cl because they make a solid. So ionic compounds are always solid at room temperature. So it's this freestanding solid because the particles are all very specifically arranged. If you want to cause that to melt down, you've got to break that arrangement. That means you need to add a huge amount of heat because you've got to take all those ionic bonds and break them. So yeah, ionic is always higher than covalent for melting point. Nick? Breaking them? No, yeah, the intermolecular attractions break way before ionic bonds. Because intermolecular attractions are not even, they're not even close to the strength of a normal ionic or covalent bond.
So once it melts, I mean, how do you know once you melt?
It'll melt down, yeah. It'll lose its solid structure.
So it could be like NaCl that hasn't broken its ionic bond, but it could not be something.
Yeah, if it breaks its ionic bonds, then it's going to relax and it won't have its structure.
But if you don't have enough energy to break the ionic, you do have to break the liquid. Then what state?
Yeah.
What state would it be?
Will it stay liquid, are you asking?
You know, I'm asking what state would it be?
If you have enough energy to break intermolecular attractions.
Not.
We're talking about two different things. This is held together with ionic bonds. This is held together with intermolecular.
NaCl on the other side?
All ionic compounds are.
Yeah, so like, yeah, that's what I'm asking.
Yeah, so between ionic and a network solid, network wins. Because network is one big molecule, and covalent bonds are harder to break than ionic bonds. So we're not talking about breaking the H away from the F. We're talking about breaking one HF away from another HF. Okay. Okay. Now, the last thing, we have to move real fast because I still got formal charge to talk about. But too many questions. That's why we get behind. I'm responding to your question earlier, not the fact that you're asking too many questions. Oh, it sounds good. Okay. Okay. Now you're out again. Which one of these has the lowest vapor pressure? This one's an easy one. Picture in your mind, lowest vapor pressure. What's going on when we're talking about vapor pressure?
It wants to really evaporate.
Liquids evaporate. And the liquid that evaporates the best is going to have the highest vapor pressure. Because it evaporates the most. So we're asked about which one evaporates the worst. In other words, which one has the particles held together the most so they don't evaporate well? Iodine. Non-polar, no hydrogen bonding. The only thing we have is London dispersion forces. That's the heaviest, so those stick together the most, so they don't evaporate. You with me? Use the solution guide. Don't feel like a failure if you're looking at the solution guide for these. But do give yourself the particle model. Understand what's going on in these processes. Hey, Nick. It doesn't say of a gas. Yeah. So Cl would have the highest vapor pressure because it's a gas. Yeah. Yeah. So that would be like atmospheric pressure. Yes. Yeah.
What?
Already evaporated. Yes, it's very easy to evaporate. No. Vapor pressure. So Cl, there's a lot of Cl in the gas phase, so it's got the highest vapor pressure. Iodine, those particles stick onto one another. Only a couple of them evaporate, so they've got the lowest vapor pressure. Because those particles are holding on to each other. Yes. All right. Sorry, got to move on.
Mr. Moore, this thing has 10% battery. That's fine, right?
Let's do it. We're fine.
All right.
The last thing is when you have to make a dot structure of a substance, and it turns out that there's more than one legitimate dot structure that can be made. You need to determine which is the better one. And that's why we use this topic, formal charge. You have to determine the formal charge of all the elements in that structure. And we have to do it in 10 minutes.
It's in the chapter 2. It's chapter 8.
This is in chapter 8, yep. Did anybody pre-read this one and think that it made sense? Did it make sense to you? So if we don't get through this in enough time, then I think the Zoom dolls do a good job of describing this, and they give examples, and it's not very hard. So for every element, you need to determine its formal charge, and you do that by subtracting two numbers. And that's what it's talking about right here. And my friend here, Mr. Newton, gives a description of the second number. Let's read this up.
We share the same one.
Do you really?
What?
Cool. Tuesday?
Rare.
Don't share with anybody yet.
It's either like 4 or 1 you got the average. Never that.
So I'd like to go through two examples with you. They require you to write dot structures, and I'm going to just do those and not walk through them with you. And then we'll talk about how to find the formal charges and which structure is better, which structure is more stable. The reason that we care about formal charge is sometimes when you make a dot structure, even though everybody's following the octet rule, which makes it legitimate, sometimes covalent compounds will cause, the way that we write a covalently bonded compound, it will require one of the nonmetals in there to lose some of its electrons. Nonmetals don't like to lose electrons. They hang on to their electrons. even if one is more electronegative than the other one, they still tend to hang on to their own electrons. So when you wind up with a positively charged formal charge, then it's not stable. So, can I change? Let's take a look at our first dot structure. I'm just going to give you the dot structure. That's what we have to do. Now, while I'm giving the dot structures, I want you to write this down up here on the top. The preferred dot structure is always the one that has 0 formal charge for all atoms. That's what is the best case, 0 formal charge. If you can't get everybody to 0, then what you want to try to do is get the most electronegative element to be the negative. So somebody has to gain electrons to be negative. Make it the most electronegative.
Bless you.
Ah. This ion is called the cyanate ion. Cyanate, so it should be written OCN. There's a problem involving this one in the book too, number 104 I want to say. This structure can be written with the carbon in the middle a couple of different ways. There's actually a third way to do it too. It would involve having a triple bond on the oxygen, but triple bonds on oxygen are very rare, so I just left it off. We have at least 2 different legitimate dot structures. I mean, you look at this, both are obeying the octet rule. Is one better than the other?
Mm-hmm.
Well, we can use the formal charges of the OC and the N to determine which one is better. Can you guess which one is the better? 1 or 2?
1.
One looks more stable. Okay, I'm hearing more 1s. Let's see if you're right. Let's take a look at the formal charges. Now, on the previous slide, you just wrote down how to find formal charge. You have to do it for every element. Take the number of valence electrons that element has, minus how many are assigned in the structure. So, we'll do the carbon first. Carbon has 4 valence electrons, so it's going to be 4 minus. How many are assigned to carbon in this structure? Now, with every bond, carbon doesn't have any lone pairs, first of all, so it's only sharing electrons. With every bond, both bonded atoms get 1 of the electrons. Every bond has 2 electrons. That means 1 belongs to carbon, 1 belongs to the oxygen. And since the carbon and oxygen are in a double bond, that means that carbon gets 2 of the electrons, oxygen gets 2. Okay? And over here, carbon gets 2 and nitrogen gets 2. So how many electrons are given to the carbon in this structure? Or assigned to it? 4, that's right. So carbon had 4 electrons, it's got 4 assigned to it in the structure, so, oh yeah, it's got a 0 formal charge. That's what we want. Now the oxygen, over here. Oxygen has how many valence electrons? 6. And how many electrons are assigned to the oxygen in the structure? 2, 4, 5, 6. Another success. Oxygen has 0 formal charge. Now what about the nitrogen? Nitrogen has 5 valence electrons, minus how many are assigned to nitrogen? Oh, it's not 0. It's 5 minus 6, which is a -1. And by the way, all the formal charges will add up if the thing is charged. So if we have a -1 on this thing, you can't have zeros on everything. Something's going to have a -1 because the formal charges always add up to the charge on it. So if it's neutral, the formal charges add up to 0. Now, okay, so this looks pretty good though. We've got 0, 0, and -1. Let's take a look at the formal charges of this structure over here. Yeah, so in a bond, both the bonding atoms get 1 of the electrons. Let's do this again too, over here. So how about the carbon over here? Its formal charge is going to be 4 minus, how many electrons are assigned to it? 1, 2, 3, 4. Okay, again, good, 0 for carbon. Oxygen, in this structure, is going to be 6 minus, how many are assigned to it here? 7. So the oxygen this time is -1. And the nitrogen is 5 minus 5, which is 0. Okay, so in both cases, we're going to have 2 zeros and a -1. You still like number one better?
Yeah.